Today, we want to start off by looking at what we know so far. So this is the general problem flow that we've built, and we're going to use this as a basis to build everything else that we do. And the great thing about this is that there's only one place where we're actually doing an operation, where we're doing a process that we need to learn. So if you were to recall, we started off looking at a linear system. I chose this because linear systems are nice and familiar. We can imagine just two lines and trying to find where they cross. And then we take the linear system and build it into an augmented matrix. This takes out a lot of the extra noise. We say if we're just going to be organized about things, instead of writing the x's and the y's and equal signs, let's just keep track of the coefficients and the constants where they need to be and just keep organized in an augmented matrix. Then we take that augmented matrix and find the reduced row echelon form. And then we take the reduced row echelon form and go back to an equivalent linear system, which we call the general solution. So there are some parts that we need to make sure we have. This part right here, this is where we do row operations. This is a skill that we need to practice. So we need to learn how the row operations work and the order by which we do things. We actually get an assist on the row operations part. Calculators are very good at this. I think I have one up there. It's very good at finding the reduced row echelon form of a matrix. All we have to do is learn the syntax with the calculator, and then we are done with that process. And then we also have to learn how to translate from a system to the matrix, and then from a matrix back to a system. And then we write it as the general solution. So remember that for the general solution, what we want to do is solve for the basic variables in terms of the free variables. Write the basic variables in terms of the free variables. We want to write the basic variables in terms of the free variables. The basic variables correspond to the pivot columns. The free variables correspond to non-pivot columns. The reason that I want to use this for a basis, the reason I choose to start linear algebra here is that it begins with linear systems, and we're very familiar with linear systems. That's the only reason. One of the fun things about linear algebra is you can pretty much start anywhere and build out from there. If I wanted to make the class sound more sophisticated, I would have started off with vector spaces. And then we would take vector spaces and we would just put them into an augmented matrix by describing them as a bunch of vectors. And then if we wanted some information about this vector space, we would find the reduced echelon form. So it all comes down to this eventually. Let's start with something that we're familiar with. Here's what we want to add. So we want to add some stuff. We want to start thinking about vectors and linear combinations. We want to take what we already have and start looking at it through the lens of vectors and linear combinations. And then we're going to take our vectors and linear combinations and we're going to track that up into a linear system. And then we're off to what we already know how to do. I know some of you might be shaky on this whole row operations thing. That's okay. That's a skill that we're going to be building this whole time. So it's okay to move on. We can't wait for full understanding before we move on. Otherwise, we'd just be here for like years, but just to get to chapter 3. Oh. I'm sorry, we skipped chapter 3 because it's determinants, and determinants are terrible. So today we want to look at vectors and think about linear combinations. And we also want to think about matrix equations. I didn't leave myself enough room. Oh, that's all right. And the matrix equations are just going to make us think about linear systems, which is going to make us write an augmented matrix, which is going to make us find the reduced echelon form, which is going to lead us to a general solution or some other form. Matrix equations are also going to be connected to vectors. So these are the things that we want to add. So let's talk about vectors. That's what we want to talk about today. What is a vector and what are we going to do with them? That's the important part. So for our purposes, this is a math class, this being a math class, a vector is just going to be a column of numbers. It's just going to be a column of values. We just want to think of vectors as a column of values. One of the things you might remember about vectors, some of you I know have been through physics courses. So this column of values is going to denote a magnitude and a direction. That's classically what we think of as a vector. It's a quantity with a magnitude and a direction. So it's a column of values denoting a magnitude. Is there two E's in denoting? But there's a magnitude and a direction. 50 miles an hour is a magnitude, due south is your direction. So that's what we need to make a vector, a magnitude and a direction. Functionally, what we're going to do with them is we're just going to think of them as a column of values. And we're going to go right into an example that we had before. So recall that we had this system, x minus y equals 1, and 3x plus 2y is equal to 8. So this linear system, we know will produce an augmented matrix. So linear system has an augmented matrix, 1, 3, negative 1, 2, 1, 8. We had a reduced row echelon form of this augmented matrix, 1, 0, 0, 1, and I think the solution was 2, 1. And that led us to the general solution. That's what we did with this problem so far. Linear system to augmented matrix, performed row operations to get the reduced row echelon form, and then we used the reduced row echelon form to write the general solution.
Excuse me.
Yes?
X2 is y or x1 is y?
Oh, I switched halfway through. X1 is x and x2 is y. The problem grew up from elementary algebra to linear algebra all in one line. Now it's pretty fast. So what I'm going to do is I'm going to take this linear system and I'm going to write it as a vector equation. And I'm going to have a vector for the x's, a vector for the y's, and a vector for the constants. So I'm going to say this, we can write this vector as a vector equation by saying x is multiplied by the vector 1, 3. Y is multiplied by the vector -1, 2. And I want this to equal the vector 1, 8. There's a vector equation that is asking the same question as the linear system. This vector equation is asking the same question as the linear system. So there's a lot that I did not say about what we do with vectors. What does it mean to take x times the vector 1, 3? It looks like what we do is take x times 1 and x times 3. That's how we make a scalar multiple of a vector. What does it mean to add a couple of vectors? Well, it looks like I'll have that x, 1x and 3x vector, and if I add it to the -1y plus 2, and then the 2y vector, I should get the 1, 8 vector. So just based on this example, we can see how operations on vectors should work. So note that turning this expression into this linear system demonstrates how scalar multiplication and vector addition works. So we want to make a note of that. So note how scalar multiplication and vector addition work. I usually just do this to introduce scalar multiplication and vector addition because it works exactly how you think it would work. If there's an operation that's going to be weird, then we'll spend time going over it. But scalar multiplication and vector addition, it works exactly how you think it would work. Let's check to see that 2, 1 satisfies this equation. So if this vector equation is equivalent to this linear system, which corresponds to this augmented matrix, which is row equivalent to this reduced row echelon form, then this linear system has this general solution, which is just one vector. Kind of weird calling it the general solution, but there it is. This vector equation should have the same solution. If I take 2 times the vector 1, 3 plus 1 times the vector -1, 2, let's see what we get. 2 times the vector 1, 3 is 2, 6. 1 times the vector -1, 2 is -1, 2. And if I add these together, 2 minus 1 is 1. 6 plus 2 is 8. Just as we had foreseen. Didn't expect the Emperor to show up, but there he is. Was hoping he wouldn't show up, but there he is. Kind of like episode 9. So this demonstrates how scalar multiplication, take a vector, multiply it by a scalar, and vector addition, how to add a couple of vectors, works. Now, this is a math class, and so we need to add some more language to this. When we take x times 1, 3 plus y times -1, 2, we're making a linear combination of vectors. So what we could say is that the vector 1, 8 is a linear combination. The vector 1, 8 is a linear combination of the vectors 1, 3 and -1, 2. This is what we talk about with a linear combination of vectors. So here's another way I could ask you to solve this system or to solve this vector equation. I could say, is 1, 8 a linear combination of 1, 3 and -1, 2? Asking that question is asking, is this vector equation x times 1, 3 plus y times -1, 2 equal to 1, 8 a consistent vector equation? That's the equivalent question. The equivalent question to that in terms of a linear system is the linear system x minus y equals 1 and 3x plus 2y equals 8 consistent? So everything ties back to this linear system, which gets us into the augmented matrix, which gets us to the reduced echelon form, which gets us to the general solution. Any questions?
I have a question.
Yeah.
So by just looking at the equation, there is no way that we can say that if it's constant or not?
Depends on the equation. Sometimes we can look at an equation, we can see it's not going to work out. But in general, if there's nothing here to indicate that there is or isn't going to, actually, I can look at this one, I can see that we're going to have a unique solution because I see there's only 2 vectors and one vector is not a multiple of the other vector. So I know I'm dealing with 2 different lines. The lines are going in 2 different directions. And so I know they're going to cross once. So sometimes we can tell if a system is going to be consistent just by looking at it, but not always. And so this is how we can check.
Thank you.
Actually, using that, let's point out the following. Remember that vectors indicate direction. So if we look at this vector 1, 3, in the x direction, we could think of these 2 equations. There's a 1 and a 3. So that's indicating the direction, how much the run is for each of these lines. I get to say rise and run because we just got lines in 2 dimensions. So over here are the 2 rises, and we can see that the rise over the run and the rise over the run is going to be different for these 2 lines. So we know that this is going to give us a consistent system because we know that we're dealing with non-parallel lines. Sometimes we can, and we're going to want to look for those things because an important thing to learn in a math class is, actually the most important thing about math classes is to learn enough of the math so that you don't have to do all that math anymore. You didn't take arithmetic class, so you could still do arithmetic by doing, by doing that FOIL method. You learn the arithmetic so you don't have to do that anymore. That's the point. You know what I mean? That's why we do these things, so we know what to look for so that we don't have to do all this math. That whole algebra class that you took, the whole point is not having to do all the steps in the algebra class. I know this runs counter to what you may have experienced because the teacher's like, oh, show all steps. At which point, I mean, you can go malicious compliance and say, all the steps? Really? All the steps? And then the teacher will be like, oh, no, just the ones that I wanted you to do. That's why when I ask you to show your calculations, it show your calculations. What do you need to write down to get to the answer? Because if I ask you to do 2x plus 5 equals 13, if you can see that the answer is 4 right away, just write x equals 4. That's the point of the math class. But if you personally have to say, I subtract 5 from both sides, and then I'll divide by 2, then you need to still write that. and I applaud your efforts to do so. But if you look at the equation and you can tell right away what the answer is, just write that down. That's the goal. You know what I'm talking about? What I'm saying is your algebra teacher was probably nuts. I don't want to blame them too much. They probably weren't very good at algebra. I know you probably couldn't see it, but after I said that, I took a haughty sip of my coffee. And I hope they all realize I'm just making fun. I mean, we're just having fun here. Like if I'm like, oh, well, your algebra teacher wasn't very good at algebra, and then I take a sip of coffee, and they're like, oh, ha, that's funny. Then I know everything's cool. But if they get really mad, I know one person who ain't very good at algebra. You know what I'm saying? All right. This is what we mean by linear combination. This is a vector equation. All of this leads up into a linear system, and we know where to go from with a linear system. Let's pause the video here and talk about matrix equations, specifically how to multiply a matrix by a vector. Next time on linear algebra. And then I show scenes from next week. But it's not next week, it's like 5 minutes from now.